All right. So, guys, why don't we start here and let's talk about where we're at so we sort of have a sense of where we're headed here with these papers. Whoa, what is that? That is So, guys, these papers that we wrote, this is what it looked like last year. We way overdid this. So that is absolutely not what I want. So let me grab this. I hope that's not the one that I pasted. But, oh, there we go. Okay, so I need to get rid of this, and I need to grab a hold of this. And now we've got the document that we need. Okay, so guys, relative to this entire writing project, and I want to answer your questions as well. But guys, this is where we're at. You have actually a page on top of this. And the page on top of this that you have is this guy, where you were just writing simple answers to these questions about the Nova Science Now video and how we make super heavy elements. I'm going to grab this from you in a minute. Do you mind if I do this? So, guys, just carefully remove that, leaving the staple in your packet. But if you would pull that off, make sure your name's on it, and I'm going to collect that from you when we're done with this. But guys, what I'd like to do for the next couple seconds then is I'd like to talk with you now, finally, formally, now that we're ready to get going, about what this writing project is all about. So, guys, I hope that you're sort of catching the spirit of this. Nuclear chemistry is interesting, but like a lot of things in chemistry, it can also be somewhat abstract. But guys, when we talk about nuclear chemistry, probably unlike anything else we talk about in this class, we're talking about stuff that has pretty significant and even immediate social, political, moral underpinnings. And so guys, that's what we want you to think about. This paper is not meant to be a burden. It's really just the opportunity for you to choose and then think about one of these topics relative to your informed opinions and your thinking about these ideas. So guys, these are the fundamental rules. It needs to be more than a page. But please, not more than 3. Guys, I know that some of you are very, very accomplished writers, and you take something and it turns into something big and impressive. Guys, that's awesome, but we also want to sort of keep this reasonable. So guys, we're going to go more than a page, but not more than 3. So guys, if you're working on that 3rd page and you hit return and go to page 4, find a place to wrap this up. If you bleed over a little bit, that's great. But guys, let's sort of keep it reasonable. You know the rules, 12.1 inch margins, that sort of stuff. But then guys, it's going to be about organization. And these are the things that we're going to ask you to do. Remember, what you're writing here is really kind of a position paper. And so, guys, what we want you to do, and this is the way these are going to be graded, guys, we want you to start with a thesis. What is your idea? We should use nuclear in our energy future. We shouldn't use nuclear. We were justified in dropping the bombs on. You get the idea. State your thesis. Then, guys, after that, and this is important, we're going to ask you to argue against yourself. We're going to ask you to write what is called an antithesis. Hey, I believe that nuclear energy should be a part of our energy future, but I understand that there's arguments against it. Bill Nye came out and said that the regulation over nuclear waste is completely insufficient, and that would mean and develop the other side of the argument. Hey, but then guys, this paragraph ends with a statement of why you still hold your beliefs to be true, even though you understand the opposition. Then guys, you're going to do 3 at least organized paragraphs where you're going to support your thesis. These are the reasons why I believe nuclear belongs in our future, or maybe why you don't. And then guys, finally, you're going to write a conclusion paragraph. But guys, that conclusion is not going to be you just simply restating your ideas. It's going to be you talking about why this matters right now. So guys, that's going to be the overall structure of your paper. Guys, we're going to do a works cited page. It's going to be 3 sources in addition to the Manhattan Project, the Eyes of Nye, and the Schallenberger video. You're welcome to reference those, but you need to find, and you will cite those if you cite them. But then guys, you need to find 3 other sources, and you're going to create a final page that is a works cited page. Then guys, obviously we're basically not going to turn in stuff that has underlines because Microsoft Word or Google Docs or whatever realizes those are mistakes. Full sentences, punctuation, spelling, all of that good stuff. And then guys, finally what you're going to do is you're going to take your notes pages from the movies that we watched, and you're going to staple that to the back in addition to your works cited page. So, hey, how are you? Good. So guys, thoughts or questions or concerns about that? Can I clarify anything? So guys, what if you need help with this? I would be more than happy to help with this. In addition to that, we pulled this together in conjunction with our English department. They know that you're doing this, and they have offered openly to help. So if you get into the middle of this and you're like, I'm not sure how to do this, go talk with Rep, go talk with Ellingford, go talk with Packer. It doesn't even need to be your English teacher. Guys, the English department is more than happy to help. Me and Miss Call would be happy to help. But guys, understand at the end of the day for you, these are due next Friday. So you have 8 days to pull these together. Now guys, understand on that day on Friday, I need a printed copy. Don't email them to me. I've got to have a printed copy because we are going to send these papers to the same graders that the English department uses, and they're going to be graded off campus. So I can't do anything with a digital copy because I need a physical copy to send over to BYU. Yeah. Yeah, if you'd like to, that's fine. Absolutely. But and if you don't have a printer, you could, ahead of time, email it to me. I can print it for you, or you can go to the library. But yeah, if you want a digital, that's fine too. I'd be happy to see that. So, guys, any questions about this? Okay. So then, guys, let's do this. Turning the page, guys. These are your perspective prompts. These we actually wrote not just in conjunction with the English department, also the history department. So guys, we got together with the history department and talked with them about, especially in the context of U.S. history, how could we approach this in such a way that it would be tying into the things that Reggie and others are doing in the history department. So guys, as you know, question number 1 is basically about the idea of, do scientists have a responsibility to shepherd their discoveries? And guys, that doesn't apply to what happened during World War II. This is genetic cloning right now. Guys, we could actually be getting really close to cloning people, but we don't because of the moral implications. So, do scientists have that responsibility? There are follow-up questions there. Guys, question number 2 is about whether we were justified on dropping those weapons on Japan, and whether you think we were or not. It definitely changed the power dynamic of our world. And so, guys, the questions then become, how does that inform your understandings of where we've been and where we are now? The Bay of Pigs, where it just about went nuclear with Russia. The whole Cold War thing. And then, guys, finally, what's going on in Ukraine? Get up to speed on that because there's some interesting stuff going on in Ukraine. And then, guys, down at the bottom, the idea is about nuclear power generation and should nuclear be a part of our future. So, guys, with all of that said, I believe that I'm at the point where if we don't have questions, I feel comfortable sending you out to start to get to work on this. So guys, questions, clarifications, things that you need more feedback on. You're okay? We're good? Okay. So guys, if that's the case, we now have 8 days. I would love to engage if you need more support on this. But guys, this is what we're up to, and we'll turn it in on the 8th. Or I'm sorry, on the 4th. You guys good? Okay, so don't put these packets away. Guys, take your packets and turn them to the place where you took notes on the Eyes of Nye video. You'll see why in just a minute. So you guys are on Eyes of Nye. Let me get rid of this. Let me put this away. Let me put this away. And then guys, I'd like please to gather up those papers from you. That was the front page of your packet. If you would please hand these to the aisle, and I'll gather them up from you. And then we're going to get going on what we're going to do today to wrap up the unit. Thank you, my friend. Thank you, boys. Thank you. All right, Brandon, thanks. Thanks. All right, thanks, Kyle. And there we go. All right. Hey, so guys, if you didn't turn this in, this is an activity and not a homework assignment, which means it's due at the end of the quarter. So that is not a homework assignment. So you have more time to turn it in. So guys, we're going to do this for 2 minutes, and then we're going to wrap up the unit for about 30 minutes. And then guys, you're going to have time to get your homework done and a bunch of other things, whatever you need to do. But guys, this is now where we're at. We are now on the 27th, Thursday, and we are wrapping up this unit. Now, guys, what we're going to do today is we're going to talk about a concept called half-life. You first saw this in the Eyes of Nye video, which is why I ask you to open to the Eyes of Nye video, because, guys, some of you are going to either change or more strongly support your position on nuclear power generation based on what we're about to talk about with half-life. When you first saw this, you didn't understand it. But guys, we're going to understand it better today, and it may change your position. So guys, we're going to do half-life today, but then guys, realize that this comes back to Monday, and it comes back to our test. So guys, remember the test is when all your late homework is due, and I'm realizing I haven't yet posted the study guide, so I'll do that before the end of the period, and the study guide will be there as well. Yeah? All right. Guys, here we go. Grab your notes paper, grab a periodic table, and this is us for the next few minutes. Dun, dun, dun. So guys, it goes like this. We are going to talk about half-life. The date today is the 27th, if you want to keep your notes organized. And guys, we're going to dig into this, and we're going to better understand this idea of half-life. Y'all set? So, guys, let me use this as a way of introducing this idea of half-life to you. And we can also use it as a little bit of test review as we go. So, guys, you may remember that this is the graphical representation of the back page of the decay homework assignment. And, guys, on that page, we started with uranium with a mass of 238, and we went all the way down to lead with a mass of 206, and we wrote out all the decay processes that get us from one to the other. And so what we learned is that sometimes uranium and its daughters go through alpha decay. Sometimes uranium and its daughters go through beta decay. But guys, at the end of the day, when all of these decays are over, we end up down at lead 206. Now guys, let's review really quickly for the test. Guys, remember that when something goes through alpha decay, its atomic number goes down by 2. So 92 uranium turns into 90, which is thorium. But then, guys, the other thing that happens is the mass goes down, but it goes down by 4. So in alpha decay, the atomic number goes down by 2, and the atomic mass goes down by 4. And then, guys, in beta decay, you'll notice that the mass does not change. So, guys, there is no change in mass during beta decay. What's happening is neutrons are becoming protons, so the atomic number goes up by 1, but the mass does not change. You're going to obviously see that on the test. But guys, that then provides us the life history for uranium. So it goes alpha, beta, beta, then a bunch of alphas, then beta, beta, alpha, beta, beta, alpha, and it ends up at uranium-206. So guys, thoughts or concerns about that? You will be seeing information like this on the test. So guys, this then is how we're going to wrap up the unit. We're going to answer one more question. And that question is this: how long does this take? How long does it take from uranium to get all the way up there, all the way down to lead? And guys, the answer to this is strange. How long does it take to get from uranium to lead? And the answer is instantaneously, but sometimes never. And so guys, this is what you've got to understand. These decay processes happen in a blink of an eye, but they all don't do it at the same time. If you've got a chunk of uranium, some of those uranium atoms have gone through alpha decay, and some of them haven't. And then when this turns into thorium, some of those have gone through beta decay and some of them haven't. And some of these have gone through beta decay and some of them haven't. And some of them have done this and this and this and this and this, and some of them haven't. So guys, the trick here is we can't talk about how fast this happens for an individual atom. Because some of these atoms are parked right here and they haven't changed. And some of these have gone and they're all the way down here and they're done. So guys, we can't talk about how fast this happens for an individual atom. So what we do instead is we talk about how long it takes for half of the atoms to do this. So guys, the idea then becomes this. If we have 1,000 uranium atoms, some of them change instantly, some of them will not change ever. But half of them will go through this alpha decay in 4.5 billion years. And guys, that's what a half-life is. Half of these will turn into this in 4.5 billion years. So that means after 4.5 billion years, we now have 500 of these, and we now have 500 of these. But then, guys, when they turn into thorium, they change. And some of these go through, half of these go through decay, but it happens in 24 days instead of 4.5 billion years. And so, guys, the idea is we can't predict when one of these atoms is going to go. So we talk about half-life, and that's the time it takes for half of them to go. And guys, this is what we're going to talk about today. It's the conceptual idea of half-life. So guys, let's dig into this. Grab something you can write with, and let's dig into the stuff that you need to understand about half-life. So guys, what I want to do is I want to start for you by defining what half-life is. So guys, I would encourage you to scratch this down in your notes, and it goes like this. So guys, half-life is a measure of the rate of radioactivity. But guys, given what we just talked about, these ideas should sort of ring true for you. So guys, the problem is this. Atoms in radioactive material just spontaneously break apart. They decay. But we can't tell when that's going to happen. Some of them do it instantly, some of them never do it. And guys, that creates a problem. So half-life is a measure of radioactivity, and the atoms in radioactive material just spontaneously break apart. They decay. But again, it brings us to a problem. We can't tell when an individual atom will decay. It's truly random. By the way, guys, when you're done with this little set of notes, you're done taking notes today. The rest of it is just digging into these interesting concepts. So I'll pause and let you catch up. You guys okay? All right. So guys, this is what we then end up doing. We end up talking about fractions. If we can't tell when an individual atom will decay, what we do is we talk about when a fraction of them will decay. And guys, given the name, it kind of makes sense. The fraction that we're talking about is a half. So this then becomes the definition of half-life. Half-life is the amount of time that it takes for half the atoms in a piece of radioactive material to just break apart. So guys, when you're done writing down that final definition of what half-life is, guys, settle in for a second and let's actually make sure you understand what's going on. And then we're going to play with this graphically, and then we're going to play with this conceptually. But along the way, we're going to dig in a little bit deeper to some stuff that we learned from the Eyes of Nye video. So guys, once you're caught up to here, just settle in, and we're going to play with these ideas to make sure that you understand them. You guys okay? All right. So, guys, the first time that you ran into the idea, and I know it was a while ago, but the first time that you ran into the idea of half-life was during the Eyes of Nye video. And guys, in the Eyes of Nye video, they were talking about plutonium. I know this is a stretch. Do you guys remember what they said the half-life of plutonium was? Do you really? How do you remember that? Yeah, guys, 24,000 years. Let that number here, you don't need to write it down, but let me write it down just for reference. So guys, the half-life of plutonium is 24,000 years. But now guys, do this. Find plutonium on your periodic table. You see it down there? Guys, when plutonium, and this is a question you should be able to answer, when plutonium goes through alpha decay, what does it turn into? Nope. So guys, when plutonium goes through alpha decay, and guys, if you can't answer this, you're not ready for the test. When plutonium goes through alpha decay, what does it turn into? Uranium. The atomic number goes down by 2, the mass goes down by 4. So guys, when plutonium goes through alpha decay, it turns into uranium. Now guys, with that in mind, join me up here and think about this with me. So guys, we are going to pretend that this rock is pure uranium or pure plutonium. And so guys, we are going to set this rock right here, and we are going to visually create a graph. So guys, keep your eye on this chunk of plutonium. And guys, right here, this rock is 100% plutonium. Okay? Now, we are going to move through time. So we're going to let the floor be time. And guys, over here on this ledge, this is the point where all of the uranium has decayed and it's turned into something else. Get the idea? Okay. So now guys, what is the half-life of plutonium? 24,000 years. So guys, now we're going to move this rock through time. So we move this rock through time. It's going through alpha decay. It's spitting out helium nuclei. And here we are. 24,000 years later. How much of this is still plutonium? Half. That's a half-life. Right? After one half-life, half of this plutonium has turned into something, as decayed, and it's no longer plutonium. 24,000 years. Now guys, after another half-life, 24,000 years, does all the uranium go away? It doesn't. So guys, this is the way that this goes. 24,000 years, how much of this is still plutonium? 50%. But now, years, half of the half has gone away. So now, guys, how much of this is still plutonium? 25%. And another 24,000 years later, 12.5%. And another 24,000 years later, 6.25%. Another 24, and another 24, and another 24. But guys, the deal is this. We never get to the wall. This never fully goes away because you can always have a half of an ever smaller half. Go ahead. Are you sure? I saw the glint in your eye. Guys, that's the trick with half-life. When you go through one half-life, you've got half left. But because you've got a smaller sample, it decays more slowly. And now after a half-life, it's 25, 12.5, 6.25, but you never get all the way down to 0. Guys, some of you are good enough at math that you understand the name for this. Guys, what do we call a graph that never finally makes it to a point? It's not a limit. It's an asymptote. Guys, 0 is an asymptote. This will never go to 0. We will always have a little bit more left that will then break down into a little bit more, and we never make it to 0 because you can always have a fraction of a smaller fraction, and as a result, we never get to 0. Does that make sense? This is where this gets disturbing, and then we're going to talk about Bill Nye. Now, guys, with your new understanding, do this. After a half-life, 50% of this is still plutonium, right? What's the other half? Uranium. Guys, don't miss this. When this decays, it's not like it turns into something that's safe. 50% of this is still plutonium, and the other 50% is now uranium, and that's deadly too. So guys, this gets even more dire when you realize that it's not like when plutonium decays, it just turns into something we can tuck in our pocket. Guys, it turns out that when plutonium decays, it turns into other deadly stuff. And this is where this video becomes all the more significant. So guys, we're going to go back and we're going to watch about a minute of this Bill Nye video, and we're going to let him take a swing at this. But before we do, guys, let's make sure we're clear. You don't need to write these down, but make sure you can answer the question. So guys, when things go through radioactive decay, where do the atoms go? What happens to the atoms that have decayed? Well, guys, after each half-life, a half of the sample remains, but the other half is decayed into other elements, which many times are also deadly. Are we good on that idea? Then let's let Bill talk about it. So guys, this is when you first encountered half-life.
Plutonium is the most dangerous thing that human beings have ever made. It will probably be our demise. A millionth of an ounce, the size of a speck of dust, if inhaled, will cause lung cancer. A few pounds.
So guys, I'm going to let this video play through once, and then we'll tear it apart.
The size of a grapefruit you can hold in your hand will bring down a city if used in a nuclear weapon. And it has a 24,000-year half-life.
We measure radioactivity in what's called half-lives. You see, the atoms in radioactive material spontaneously just break apart or decay. Now, we can't tell when an individual atom will decay, but we can tell when a fraction of them will. So a half-life is the amount of time it takes for half the atoms in a piece of radioactive material to break apart. Now, plutonium has a half-life of 24,000 years. So let's say this red water is the plutonium in a spent nuclear fuel rod, fresh from the reactor. Well, after one half-life, 24,000 years, diluting this water by half, it looks like this. After two half-lives, 48,000 years, it would look like this. After 10 half-lives, 240,000 years, the water starts to look pretty clear. Now, plutonium is notorious. It's especially radioactive. It's 20 million times more radioactive than uranium dug from a mine. You see, we're not talking about potato salad left out in the sun. We're talking about plutonium. Now, the legal requirement for storing this material is only 10,000 years. That'll be over here someplace. That's not even half of a half-life.
So guys, let's pause. Let's really tear this thing apart. And then I want to give you a moment, if you would like, to take your new understandings and include them in your Eyes of Nye notes, if this is pertinent to what you're planning on writing towards. So guys, to get started, let's go here. And guys, let's talk about how this analogy is all set up. So questions for you. What does the red food coloring in these bottles represent? Plutonium. So guys, just like my rock sitting here on the countertop, this bottle right here represents plutonium, pure plutonium, plutonium. But then guys, what do the cinder blocks represent? Half-lives, 24,000 years. So how then did Bill create this visual? And what he did is he took the water that was inside this bottle, well, he had more of it, but he took water at this concentration and he diluted it in half. So after one half-life, half of this is still plutonium. Then he took this, diluted it in half, and now it's a half of a half, so it's a fourth red food coloring water. And then it's an eighth and a 16th and a 32nd and so on. So, guys, every time you see that bottle move to the right, it is half as concentrated. But guys, we also now understand, you'll notice that the volume is not decreasing. So the stuff that is no longer plutonium is now uranium, and we're not even talking about that reality. But again, guys, the cinder blocks are 24,000 years. You good? Okay. So guys, here then is the question. Let's allow this to move forward, and you can physically see the red water getting lighter and lighter. I don't know why my board's cutting out. Lighter and lighter and lighter and lighter. So guys, let's go down here. So imagine this. Guys, if this red water were poisonous, certainly none of you would be dumb enough to drink this. But here's the question. Would you be willing to drink that? Still red. Guys, I still see a hint of red. How about down here? Maybe. As we get down here, we start to think that maybe this is safe enough that we would be willing to interact with it. But guys, remember, every cinder block is 24,000 years. So we are talking about hundreds of thousands of years into the future before this stuff becomes safe enough that we'd be willing to interact with it. But guys, this is where this really gets sobering. Guys, the question is this. What does Bill's hand represent? Say it again. 10,000. But why 10,000? Where did that number come from? Yeah. Guys, that's the law. The law is that we have to be able to store this plutonium for 10,000 years. That's ridiculous. Guys, that's not even half of a half-life. And when it's over, our plutonium still looks like this, and the stuff that ain't plutonium is uranium. Guys, 10,000 years is a meaningless number. But where did 10,000 years come from? Do you remember, Adam?
It's kind of arbitrary, right?
It was completely arbitrary, but I won't comment. But there was a reason behind, it's an arbitrary reason, but it's a reason. Close, because we're using those as examples, but it was more government bureaucracy. Do you guys remember? So here's the question. Where do we put this stuff when we store it? In big metal containers, right? And their studies were showing that those metal containers would fail in 11,000 years. So they said, if we know those containers will fail for 11,000 years, let's make the guideline 10,000 years, and now our containers meet the law. But guys, that law has nothing to do with chemistry, because 10,000 or 11,000 years, guys, this stuff is still deadly on a magnitude that we have absolutely no idea how to deal with. Guys, 10,000 years was a completely arbitrary length of time that just allowed our containers to be legal. Do you understand this now? Guys, do you want a second to jot some notes in your eyes of Nye thing, especially if you're writing about nuclear power? Because this is an amazing point relative to whether or not we should be using nuclear power. So let me give you a second to jot this down, if you'd like. If not, it's fine. Only if it meets your needs. But then, guys, after this, now that we understand the concept of half-life, and now that we understand some of the crazy politics of half-life as it applies to nuclear power generation, guys, we're going to look at this graphically, this whole idea of an asymptote. And then, guys, we're going to talk about this a little conceptually again. And it's going to turn into a little bit of math, and then we'll be done. So guys, if you are writing towards the nuclear power generation question, I would suggest to you that this is important information regardless of what you think. Because if you're anti-nuclear, man, that's a strong argument. But if you're pro-nuclear, you still have to deal with this reality, and you'll do that in your antithesis. So one way or another, if you're writing about nuclear power generation, this should play into your thinking in one way or the other. So do you guys need more time? You okay? All right. So guys, let's do this then. So we've looked at this whole idea of half-life from a couple different angles. But guys, what we're going to do now is we're going to look at it graphically so that you have a better idea of this idea of asymptote. So guys, when we started teaching this material, 5 or 6 years ago, I found this graph. And I used this. I thought it was a brilliant representation of the material that we're talking about. And as you look, we've got numbers of atoms, and that's in millions. And then we've got half-life, or we've got time that moves on in years. And each one of these represents a half-life. And so we can see the amount going down and down and down over time. And we now understand that 0 atoms is an asymptote. We'll never get to 0 like the wall, because we can always have half of an ever smaller half. And guys, I shared this with my classes thinking, man, this is a great way to explain this. And I had this group of particularly bright students, and they looked at this and they're like, we don't like that. This is not a good representation of half-life. And guys, it was awesome. They took this graph and they picked it apart, and they're like, no, this doesn't represent what you're helping us understand. So guys, I would turn that thought then to you. Guys, pick this graph apart. Talk with the person next to you about what's wrong with it. Why? Where are the weaknesses in this graph? And what could we do to make them better? Chat about it for a minute. or think about it for a minute and then chat. What do you see? Because where are the misrepresentations, the mistakes in this? Yeah. Oh, brilliant. That was the one that drove them nuts. Good for you. Guys, sorry. Not a good time for a lifesaver. Guys, I love what TJ is saying. So we got 10, right? 2, 4, 6, 8, 10. So guys, we've got 10 of whatever this element is at time 0. And then after a half-life, we've got 5. But TJ, like this other class of students I was working with, is like, where are the other atoms? They don't just go away. If this is plutonium, they don't just vaporize. There are still... Sorry, this isn't drawn to scale, but guys, there are still these other atoms left. They haven't disappeared. They've just turned into other elements, and these other elements can also be deadly. So guys, they brought that up. But then when we really started digging into this, we found even smaller mistakes. So guys, let me ask you this. What is the half-life of this element from this graph? You can't. Why not?
Because it's only 10, 20, 30.
Right. But even if we're measuring and making estimates, given that, what would you call that? Like 12? So if that's 12, then if this is 25, the next half-life should be 24, and it's on the wrong side of 25. And if that's the case, the next half-life should be 36, and they put it above 40. So guys, these time spaces should in fact be even, and they're not. And they're like, wait a minute, we thought half-lives were a fixed unit of time, and they are, and they're not representing that here. Guys, other things, well, do you see other things? Other things that my other students picked out was that, and this may get a little nitpicky, but they're like, wait, why does this curve follow the top of the balls and this one goes through the bottom? Shouldn't it be up here? And I would argue yes. Oh, that's interesting. So really, technically, I never thought of that. So yeah, Adam, that's interesting that really these balls, sorry, I'm not doing a good job, but they should be on the line rather than to the right of the line. That's an interesting point. I'd never thought of that. Guys, other issues with the graph? Yeah. Yeah, so it never says, and it's somewhat arbitrary, right? And so there's really no way for us to error check the half-lives, even though we know they're wrong, because there's no way for us to know, right? Other thoughts? So guys, let me then offer you this. Am I drawing dots? My board is really struggling after the last update. Better? This was actually a representation. I didn't draw it, I found it. But after my students' ideas on corrections, and I sort of found this on the fly during class, together we kind of decided that this was maybe a better representation. I think it checks most of the boxes. Guys, notice that down here we still have 0 half-lives, and we have a scale that's proportional. So we've got 25, 50, and 100. You'll notice that they actually gave us something close to the fractions, because this should be 12.5 and this should be 6.25. So they even provided us those smaller breakdowns. But But guys, this was the part that was, and I can't touch this. Guys, this was the part that was especially attractive to us, was the fact that now, like TJ pointed out, here we have 100 of these whatever they are's. And guys, if we actually sit and count them, you'll find out now there's still 50 of them. But now there's 50 of the grays. And then guys, when we get down here, we've actually got 25 and 75. This one they didn't like because there should be 12 and a half of the red ones, understanding that you can't have half of atoms, so they represent it as a whole atom. But guys, I would suggest that this does a better job of representing this graphically. So with this as a foundation, is it feeling more comfortable relative to what half-lives are really all about? Okay. So guys, this is how we're going to wrap up the day. At this point, what we used to do is throw equations in front of you that represent mathematically how half-life works. Guys, the equations are exponential forms, they're fractional exponential forms, and we finally decided that as you go on into your adult lives, you're never going to remember the math, but you will remember the logic. So guys, we are going to teach you to solve half-life problems logically. So guys, don't write this down, but I would encourage you to write down the answer because you're going to see 2 of these questions on Tuesday's test. So guys, read this through with me. It says 50 grams of plutonium decays for 72,000 years. The question is this: how much of this plutonium is still around at the end of this period of time? So if you start with 50 grams of plutonium, let it sit around for 72,000 years, which is 7 times the legal limit that we have to store this stuff, remember? How much plutonium is still left at the end of the time? Guys, we're going to solve these logically. Draw a rock on the left-hand side of your paper. Guys, you're literally going to be drawing rocks on the test. So guys, this rock, like this rock, represents your sample, and this sample weighs 50 grams. By the way, guys, if you are interested in the math of this, we do teach it in AP, but we don't do it in here. So guys, we start with a 50-gram rock, and we allow this rock to go through 1 half-life. But how long is a half-life? 24,000 years. So we're not done. We need to let this thing sit for 72,000, and we've only let it sit for 24,000, so let's keep going. Let's go through a second half-life. After 2 half-lives, this thing, well, after 1 half-life, it now weighs 25. So guys, after a second half-life, it has now been sitting for 48,000 years. How much of it's still plutonium? Yeah, half of 25, 12.5 grams. But guys, that only gets us to 48,000 years. Let's let it sit around for another half-life, a third half-life. How long is that third half-life? 24, 48, 72. And guys, by the way, the numbers that we'll give you will always work out even like that. We won't give you fractions of half-life. To do that, you need to be able to do the math. So guys, now we are at 72,000 years. And how much does this weigh? Half of 12 and a half? 6.25 grams. But guys, again, where's the other 93.75 grams of stuff? It's uranium, and it's out doing bad things as well. So guys, that's one of the kinds of problems that you need to be able to solve, and we're going to do that drawing rocks. You okay? Here's the other type of problem that you need to be able to solve, and it goes like this. You've got a 100-gram sample of molybdenum-91, and you let it sit for 60 minutes. At the end of this time, you've got 6.25 grams of this left. What is the half-life of molybdenum-91? How do you figure it out? Draw a rock. And guys, this rock weighs 100 grams. So now we're just going to start moving through time. After one half-life, what does the rock now weigh? How much of this is still molybdenum? After one half-life, how much is still molybdenum? 50 grams. But guys, notice I asked that question really poorly the first time. How much does the rock still weigh? 100 grams. 50 of it's molybdenum and 50 of it's something else. We're just tracking the molybdenum. But guys, we're not down to 6.25, so let's keep going. Another half-life. Now it weighs 25. Still not down to 6.25. So another half-life. Now it weighs 12.5 grams, but we're still not down to 6.25. So then we go another half-life, and now we're down to 6.25. So guys, the question then becomes, how do we figure out the length of a half-life? There you go. So guys, this thing went through 1, 2, 3, 4 half-lives. But that happened in 60 minutes. So 60 minutes is how long it takes for this to go through 4 half-lives. So how long is each half-life? 15 minutes. But guys, we'd like you to please show that math. 60 minutes divided by 4 half-lives means that each half-life is 15 minutes long. And guys, you've got to be able to solve both of those on the test. There are homework questions relative to this as well. And guys, you now have the better part of 20 minutes to tackle this homework. Guys, you're going to need to do this on another sheet of paper. It's homework assignment number 3. We will look at this on Monday. We will review this on Monday. And then we will take the test on Monday. Guys, I'm going to really quickly, before I start, if you need help, Cassie, I know we need to talk. Let me get the study guide posted so I don't forget. And then, guys, again, the rest of the time is yours. Let's get this homework done. The answers are on your phone. I'll also post them on the wall. And, guys, remember, Monday's the deadline for late homework. Keep that in front of you. And let's get this homework done.